Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about energy. What is energy? And this energy is related to computational chemistry. Energy is one of the most useful concepts in science. The analysis of energies or energetics can predict what molecular processes are likely to occur or able to occur. All computational chemistry techniques define energy, such that the system with the lowest energy is the most stable. Thus, finding the shape of molecule correspond to finding the shape with the lowest energy. My friend, the amount of energy in a system is often broken down into kinetic energy and potential energy. The kinetic energy may be further separated into vibrational, translational, and rotational motion. A distinction is also made between the kinetic energy due to nuclear motion versus that due to electron motion. The potential energy may be expressed purely as Coulomb's law, or it might be broken down into energies of bond stretching, bond bending, conformational energy, hydrogen bonds, and so on. Now, chemical processes such as bond stretching or reactions can be divided into adiabatic and diabatic process. Adiabatic processes are those in which the system does not change state throughout the process. And diabatic or non-adiabatic processes are those in which a change in the electronic state is part of the process. Diabatic process usually follow the lowest energy path, changing state as necessary. In formulating a mathematical representation of molecules, it is necessary to define a reference system that is defined as having zero energy. My friend, this zero of the energy is different from one exponent approximation to the next. For ab initio or density function theory method, which model all the electrons in a system, zero energy corresponds to having all nuclei and electrons at infinite distance from one another. Most semi-empirical methods use a valence energy that corresponds to having the valence electrons removed and the resulting ions at an infinite distance. A few molecular mechanics methods use chemical standard states as zero energy, but most use a stainless molecule as zero energy. For some molecular mechanics method, the zero of energy is completely arbitrary. My friend, even within a particular approximation, total energy value relative to the method's zero of energy are often very inaccurate. It is quite common to find that this inaccuracy is almost always the result of systematic error. As such, the most accurate values are often relative energies obtained by subtracting total energy from separate calculation. This is also very important point here. This is why the difference in energy between conformers and bond dissociation energy can be computed extremely accurately. Now, electrostatics. My friend, electrostatic is the study of interactions between charged objects. Electrostatic alone will not describe the molecular system, but it is very important to the understanding of interactions of electrons, which is described by a wave functions or electron density. The central pillar of electrostatics is Coulomb law, which is the mathematical description of how like charges repel and unlike charges attract. The Coulomb law equation for energy and the force of interaction between two particles with charges q1 and q2 at a distance r1 to r is equal to q1 q2 r1 to F is equal to q1 q2 r1 to square. So these equations do not contain such as vacuum permittivity constant. Theoreticians and the software developer work with a system of unit called atomic unit. Within this unit system, many of the fundamental constants are defined as having a value of 1. Atomic unit will be used throughout this lecture unless otherwise specified. Another very useful function from electrostatic is the electrostatic potential phi. The electrostatic potential is a function that is defined at every point in three-dimensional real space. If charged particle is added to a system without disturbing the system, the energy of placing it at any point in a space is the electrostatic potential times the charge on the particle. The requirement that there is no movement of existing charge polarizations of electron density is sometimes described by stating that the electrostatic potential is the energy of placing an infinitesimal point charge in the system. The application of electrostatic potential to chemical system will be discussed further. The statement of the Coulomb's law above assumes that the charges are related by a vacuum. If the charges are separated by some continuum medium, and this interaction will be modified by the inclusions of dielectric constant for that medium. For the description of molecules, it is correct to assume that the nuclei and electrons are in a vacuum. However, dielectric effects are often included in the description of solvent effect. The Poisson's equations relates the electrostatic potential phi to the charge density rho. The Poisson equation is del square phi by is equal to minus rho. So conversion factor for atomic unit: length, atomic unit Bohr, 1 Bohr is equal to this. Weight, atomic mass unit, 1 AMU is equal to this kg. Charge, electron charge, 1 electron is equal to this coulomb. Energy, Hartree, 1 Hartree is equal to electron volt. And charge separation, Bohr electrons, 1 Bohr electrons. So this is very important conversions for length, for weight, for charge, for energy, for charge separations. Now this may be solved numerically or within some analytical approximations. The Poisson's equation is used for obtaining the electrostatic properties of molecules. Now atomic unit. The system of atomic unit was developed to simplify mathematical equation by setting many fundamental constants equal to 1. This is a mean for theorists to save on pencil lead and thus possible error. It also reduces the amount of computer time necessary to perform the chemical computations, which can be considerable. And the third advantage is that any changes in the measured values of physical constant do not affect the theoretical results. Some theorists work entirely in atomic unit, but many researchers convert the theoretical results into more familiar unit system, give some conversion factor for the atomic unit. Now thermodynamics. You know, my friends, the thermodynamic is one of the most well-developed mathematical description of chemistry. It is the field of thermodynamics that define many of the concepts of energy, free energy and entropy, and this covered in physical chemistry. You know, thermodynamics is no longer a subject for an extensive amount of research. The reason for this great twofold: the completeness of existence of previous work. So, general inability to provide details insight into chemical process. Very often, any thermodynamics treatment is left for trivial pen and paperwork. Since many aspects of chemistry are so accurately described with very simple mathematical expression. You know, the computational results can be related to thermodynamics. The results of computations might be internal energy, free energy, and so on, depending on the computation done. Likewise, it is possible to compute various contributions to the entropy. One frustration is that computation software does not always make it obvious which energy is being